We'll go ahead and begin to get started. Good afternoon and welcome to the Alfred University Bergren Forum. My name is John D'Angelo and I am a professor of chemistry and the host for the fall 2024 season of the Bergren Forum. This is episode 10. Today is Thursday, November 7th, 2024, and for those of you attending the forum online, here in Western New York, it is a gray and dreary day, but inside Nevin Theater or the Powell Campus Center, it is warm and cozy and the coffee and tea are hot and free. Before starting, we have a few announcements. First, I misspoke last week when previewing this week's forum, and it is next Thursday's forum that will be given by Roberto Che Espinoza, pastor of the Union University Church, and the talk will still be about bridging radical differences. There are some other announcements for this week. Namely, the Vice President of Business and Finance / CFO is holding open office hours every other Tuesday from 9:30 a.m. to 11 a.m. for the rest of the fall semester. This office is in Jordan Hall, if you're interested. Admissions kindly asks that you not use visitor spots, especially if it has a student's name on it. I think we would all agree, and this is my own editorialization, that is not exactly the warmest Alfred welcome we can offer to occupy a spot dedicated to somebody that we are recruiting. The Queer Art Collective is hosting a first come, first served art critique later today from 5 p.m. to 7 p.m. in Harder Hall, room 209. If you'd like to assist with midnight breakfast, which will be on Sunday, December 8th, starting at 10:30 p.m., contact csi@alfred.edu. Also, it is time for electronic waste pickup. Go to www.sunking.com/acceptable-materials for more information, or bring e-waste to your favorite academic department for disposal. Without further ado, today's forum will be given by Michaela Fenrock, Assistant Professor of Geology, and her talk will be about how computers can help us understand climate change. The floor is yours.
Hi, everybody. Sorry if you're here to hear, you came here to hear about bridging radical differences. We're going to bridge radical differences between the climate and computers, maybe. Okay. So, like John said, my name is Michaela Fenrock. I'm an assistant professor of geology. I'd like to get rid of this, but maybe I can't. That's okay. Pretend it's not there. So today we're going to be talking about the past and future of Earth's climate and how I use and other people use computers to learn about these things. Before we get started, I want to acknowledge my co-authors, Alan Condren at the Woods Hole Oceanographic Institution and Jesse Farmer at UMass Boston. They were very important to, or are very important to the research part of this talk. So thanks to them, though they are not here, I don't think. Okay, so can I do this? Hold on. There we go. Great. Okay, so what's to come for you guys? I'm going to start off by sharing my perspective, where I'm coming from with all of this, okay? My background a little bit and what I do. And then I'm going to tell you about how climate change works, specifically talking about modern climate change. So the climate change that we're experiencing today, that we exist in, how does that work? Then I'll tell you how I study climate change. That's going to be a little bit broader. It's going to be more about climate change in general. And I'll get into some nitty-gritty details there. For you, my goals are to teach you about how the climate works, okay? What is happening to our planet to make it warmer, to make climate change. And I want you to understand in greater detail what climate change research looks like. My other goal is to avoid dread. So there's been a lot of dread going around. I'm going to try to guide you through this in such a way that does not make you feel bad, okay? I've given you this sort of peaceful image of waves crashing towards that end to make you feel calm going into this. And additionally, because I'm an oceanographer. My PhD is from the Woods Hole Oceanographic Institution in conjunction with MIT, and I study the ocean. So when I think about the climate, I'm thinking about it from the perspective of the ocean. When you think about oceanography, this is what might come to mind. You might think of a wizened, bearded man sailing with a big ship's wheel. But then you might think to yourself, The year is 2024. Michaela's not that old, hopefully. And she probably doesn't do this. You might think of Jacques Cousteau, and you might imagine me in a submersible, okay? Going down to the bottom of the ocean to explore deep ecosystems, to explore cold climates, investigate really slow moving ocean currents. But then I hope you would think to yourself, Michaela would never, ever go in a submersible, not even once, okay? I know better than that. So maybe you would imagine me more safely scuba diving around a coral reef, studying fish, corals, things like that. Through some intentional choices that I made in my PhD, you would be wrong if you imagine any of this. What my research, what I do, what it looks like when I do oceanography is this. So there I am, and there's my computer. That's the important part. I do computational oceanography. So why do I do that? An important part about this is that that's Alfred, New York, right there. And then all the way over here is the ocean. Okay, I did my PhD over here, so I had the option to go into the ocean if I chose to, but I actually didn't. So oceanographers live far away from the ocean. You don't need to be near the ocean in order to do oceanography, but if you wish to make progress on your research at a fast clip, let's say, it helps to use a computer, at least for me. So for me, the ocean is in my computer. The ocean that I'm imagining is the real ocean, but as simulated through computer models. I perform computer simulations of how the ocean changes, and particularly how the ocean changes are related to climate, okay? That's the model over there. It's an orb. Okay, so my questions, specifically what I'm interested in, is if we change the ocean, how does that change the rest of the climate? The ocean has been referred to as the powerhouse of climate. I agree with that. I think that's right. Okay. So I'm interested in if you change the climate, how does that change the ocean? On the flip side of that, if we change, oh, well, that's what I just said. But anyway, both sides of it, right? If you change the climate, how does it change the ocean? If you change the ocean, how does that change the climate? I'm interested in that interplay, the interface between these two things. And then I'm also interested in examples of this in the past. So I do what's called paleoclimate. It's the study of past climates. And that's because it's helpful to have other examples of climate change. The way our climate is changing now is just one example. We can learn more about our climate system, as you'll see today, by investigating these other examples throughout Earth's history. So to answer these kinds of questions, we typically need a computer. We don't always need a computer. You can do oceanography and climate science without involving a computer, perhaps until you're writing your paper. But to answer these questions well, computers typically need to be involved in some capacity. I do the computer part. That's what interests me and how I spend my days. So before we get into that, though, let's make sure we all understand climate change, okay? So we begin with greenhouse gases. So this is a collection of greenhouse gases: CO2, methane, water vapor, nitrous oxide. Some molecules are better at storing energy, okay? Imagine I am methane, okay? I have 4 hydrogens coming off of my carbon, okay? Because of my 4 hydrogens, I can do this, okay? I can move my hydrogens around, I can bend them, I can flex them in and out. That's storing energy. I just got hot doing that, okay? So that is how an effective greenhouse gas works. It has more modes of movement that it can do, and that allows it to store energy. As we add more of these molecules to the atmosphere, okay, they're more effective at warming the atmosphere. CO2, methane is particularly effective. Water vapor is really good greenhouse gas, and it's bad, but it's good at doing it. Nitrous oxide is a very effective greenhouse gas. All of these molecules, if we add them to the atmosphere, we increase their concentration. They increase the ability of the atmosphere to flex in different ways, warming the atmosphere. So the more of these molecules we have in the atmosphere, the warmer they'll be. We hear the most about CO2, carbon dioxide, and that's not because it's any kind of special greenhouse gas. It's not more effective than methane, for example. In fact, it's much less effective. But the reason why you hear the most about CO2, about carbon dioxide, is because we add the most of it to our atmosphere. It's the most ubiquitous greenhouse gas, and every year we add the most of it, okay? So it's of concern because of how much there is, not because it's really good at warming the atmosphere, it's pretty good at warming the atmosphere, but because of how much there is. So this is called the Keeling curve, named after Dr. Keeling. This goes back to 1960 up to about 2020, okay? And this is the concentration of CO2 in our atmosphere in parts per million. In 1960, it was about 310, and recently it's been closer to 410. So we very effectively added CO2 to our atmosphere every year. These little squiggles that you might see, that's just spring, okay? Plants bloom, they pull CO2 out of the atmosphere. So that's what that is. It's helpful, but not helpful enough. Okay. So that is how climate change works now, okay? We're adding more greenhouse gases to our atmosphere. They're able to store heat more effectively than other molecules, and that warms the planet, okay? We have more CO2, so the atmosphere is warmer, so the planet is warmer. Climate change is not that complicated, okay? In terms of its causes, that was all of it, okay? We burn fossil fuels, they add greenhouse gases to the atmosphere, they warm the atmosphere. That's all there is. So when you try to understand climate change, you try to communicate about climate change, you can do it now, okay? You have all the information. What is complicated are the impacts of climate change. Warming the Earth is one thing, but what happens after that warming? What happens to the ocean? What happens to ice? Those impacts, following the thread of that warming to specific day-to-day experiences of people, which is what we're really interested in, is what's complicated, okay? So let me give you an example of that. Okay, they got that. Okay, so we just talked about this. Step one, we have more CO2 in the atmosphere, so the planet warms. This goes back to 1880 up to 2022, I believe. And this is the average temperature of the planet as compared to 1901 to 2000. So compared to sort of the middle part of this. Prior to the middle part of the 1900s, let's say, it was colder. More recently, it's been warmer. Not every year is warmer than the previous year, but on average, it's pretty easy to draw a trend line there. Warmer every year. So as the planet warms, ice melts. You might remember this from 2006's An Inconvenient Truth. I think of this polar bear as the mascot of climate change. So he tries to climb onto the ice, it breaks because it's too thin, because the planet's warmer. So he has nowhere to hunt from. This does happen. It's a lot sadder in real life. Animation has come a long way since 2006. More practically, and maybe a little bit more realistically, we can look at ice loss in this way. So this is 1985 to 2022, and this is fraction of ice, or sea ice in the Arctic specifically, and how old it is. In 1985, about a third of sea ice in the Arctic was older than 4 years old, okay? And about a third was new sea ice that regrows every year. So in the Arctic, in the best of times, we have sea ice always. In the summer, August, whatever it may be, there is still frozen seawater in the Arctic. That sea ice can last for multiple years, hopefully longer. The longer, the better. But as time has progresses and the Earth has gotten warmer, we now have less than 5%, let's say, of our sea ice is older than 4 years old. Meanwhile, more than half of our Arctic sea ice is less than a year old. So this is a really noticeable trend that we have younger sea ice and we have much less of that old important sea ice that helps us grow more sea ice. What doesn't come out in the way these data are displayed, but perhaps you can intuit, is that we also have less sea ice in the Arctic overall. Much less, in fact. So that's step 2. So step 3 is that melted ice makes part of the ocean colder. Okay, so this is a graph, or not a graph, a map, let's say, of ocean temperature compared to 1951 to 1980. You'll notice most of it is red. The ocean on average has gotten a lot hotter compared to 1951 to 1980. But there is this blue circle in the middle, or big blue blob, okay? That's called the Atlantic cold blob. That's actually what we call it. It's also called the North Atlantic warming hole, whatever works for you. When first I saw this figure, I thought to myself, perhaps there's some good news here. This part of the Atlantic is getting colder. Maybe there's some kind of negative feedback that's cooling the Atlantic, making it warm less quickly. Unfortunately, this cold blob is believed to be related to the melting of Greenland. So no good news there, unfortunately. So let's talk about it though. This cold blob right here makes part of the ocean colder. So what does that do for climate? Think about Greenland, okay? So I've zoomed in for you here. Greenland's right next to that cold blob. Maybe Greenland doesn't warm so quickly because of that cold blob. Maybe its meltwater insulates it, keeps it a little colder. What do you think about that? I see shaking heads. Yeah, well, yeah. I don't think that's a good idea. Because importantly, what about this much hotter Greenland current? So this current here, this comes out of the Arctic. It's much hotter than it has been in the past. The Arctic is warming much faster than the rest of the planet. And this really hot current, or now relatively hot current, whips around Greenland, heating Greenland right up. Okay, so maybe that's what happens, right? Greenland, this doesn't matter, okay? But what about the interplay of those two things? Does the Atlantic cold blob then cool off the Greenland current? I see a head shaking, but I don't think you know that for sure, okay? The water is fresh. Does that water change anything about how the ocean moves? So I told you just now, Greenland's melting is adding fresh water. It's melted ice, it's melted fresh water, okay? So does the ocean move differently due to this freshening? I see some heads nodding, but you don't know that. You don't know for sure. And then let's zoom out. Look importantly at all of the ocean currents that are in the Atlantic, okay? It's a dynamic system. The water that is in the North Atlantic, getting colder, that changes, for example, how the North Atlantic drifts, okay? How much warm water is transported to the Arctic? Does that increase or decrease? What about the North Equatorial current? All of these systems are complicated, okay? And if you sit here and try to think it through, try to figure it out with the power of your mind, I can feel the heat radiating from your brain, the pain that you will experience. So that's why we do this, okay? The computer saves you from that challenge. The climate and the ocean are really complicated. In order to understand them well, we do this computer modeling, okay? So, looking back at our cold blob, okay, I'll tell you, we don't really know the impacts with certainty yet of this meltwater in particular. But we can start to figure it out, as I just said, using computers, okay, using the power of simulation, and using examples from past climates. So past climates I mentioned, but just to reiterate, what's important about past climates is that they give us other examples. They give us the opportunity to check our assumptions to better understand how the ocean flows in the climate system in general, broadly. How does it work, okay? So examples from past climates are an important tool for what we're going to be doing here. But let's take a step back. The question we were just asking was too specific, okay? So let me reframe it for you. So this is a map of ocean currents, particularly in the Arctic. We're going to be talking about the Arctic today, so there it is. The North Atlantic current here, it transports heat up from the equator to the Arctic, okay? And then we have gyres swirling that go on up there. The movement of water moves heat, okay? If you have hot water, it's going to move, and it's moving. It's going to take that heat with itself to wherever it's going. This ocean flow is driven by differences of temperature and salinity. So when we think about Greenland melting over here, okay, that's where that becomes important. As we change the salinity of the ocean and its temperature, we change how the ocean flows. So if you change the temperature and the salinity of the ocean, putting those two things together, you change how heat is transported. That's climate, okay? Transporting heat where the heat is, that's how we experience climate. So now let's pose these as questions. How sensitive are ocean currents? And in particular, how sensitive are they to changes of temperature and salinity? If you change temperature and salinity, how much do you change an ocean current? And then how much do you change climate? And then finally, just to bring it back, do we have any other examples from Earth's history? Rarely, when looking for an analog from Earth's past, do we find a perfect equivalent, okay? So what I show you today is not a perfect equivalent for how I framed this talk, but bear with me. With the Bering Strait. So that's what we're going to be talking about. I didn't plan that. Okay. So the Bering Strait is right there. Okay. It's between Alaska and Siberia. It travels north. So this is north. Everything is north here. It's the only direct connection between the Pacific and the Arctic Oceans. And that's really important. This is not a very big current at all. Okay. It flows very quickly, but it's not very large. It can't be. But because it's the only connection between the Pacific and the Arctic, we care about it a lot, or I do at least. So just to give you some geographic framing, there's Alaska, there's Russia, that's the Bering Strait. Flow goes north through it. It's only about 82 kilometers wide, okay? So that's closer than it is from Alfred to Rochester. If you could drive from here to here, it would take you an hour and a half, something like that, okay? Importantly, it's only 52 meters deep. Actually, it's gonna be 53, but that's okay. The shallowness of this becomes really important in ways that I will describe shortly. But like I said, water flows north through the Bering Strait, okay? It's the only direct connection between the Pacific and the Arctic Oceans. And it's the primary source of fresh water to the Arctic. That might surprise you, but this water is way fresher than that water. That water is pretty salty. This water, it's receiving melt from glaciers in Siberia and Alaska, a lot of river runoff. So it's actually pretty fresh. Most fresh water that's delivered to the Arctic comes through the Bering Strait. Okay. Also, I'll call out for you these two little islands here. These are called the Diomede Islands. Remember them, they come up later. Okay, so looking back through time, this is sea level compared to modern. Modern's up there, 0, okay? And then this is time in tens of thousands of years, going back to 200,000 years ago. This blue line is the depth of the Bering Strait. So whenever sea level has been about 50 meters lower than it is now, the Bering Strait is land. Water can't get from the Pacific to the Arctic directly. So we're interested in that space between modern sea level and 50 meters lower than present. If you make the Bering Strait shallower, presumably less water can get through, okay? Which means less fresh water is being delivered to the Arctic. So, framing this, we want to know about how changing ocean circulation, and in particular salinity, can change climate, okay? We know the Bering Strait is a primary control on how salty or fresh the Arctic is. If you have less water coming through the Bering Strait, the Arctic is saltier. If you have more water coming through the Bering Strait, the Arctic is fresher, okay? So that is how we're getting at this question about how ocean circulation changes depending on salinity. When sea level is lower, less water gets through the Bering Strait. So the Arctic should be saltier. Okay, so that's our natural experiment that we're interested in. How does ocean circulation on our planet, or how has it changed when the Bering Strait is shallower than it is now? But by how much? So that's getting at this question, or this point, less water. It's not enough to say it's less. It's not enough to say there's less fresh water going to the Arctic. We need a numerical quantitative number, okay, in order to use this. We already said less, so we know that, but how much less? So this is our research question that we're moving forward with. If we make the Bering Strait shallower, how much water gets through? I don't, or I wouldn't expect this to be a linear process. And the analogy that I use here, which maybe you heard if you came to my ENVS seminar last year, is a garden hose, right? So bear with me. You can have the garden hose open, some amount of water gets through. You can put your thumb over it a little bit, and approximately the same amount of water will get through, but at a higher pressure, okay? The dynamics of how it goes through are different, but it's about the same amount of water over time. You can also put your thumb, depending on how high the hose is, you can put your thumb over the hose and block water and just have a little spritz coming through, okay? So think of the Bering Strait as a garden hose, okay? How much can you close it before you actually change how much water goes through? And this is what we're going to simulate, not the garden hose. We're going to simulate the Bering Strait getting shallower. It's going to look like this. So this is the sort of right out of the box simulation. Okay, you can see how deep the strait is. I have not done anything here. All the way over here at 0 meters deep, it's completely closed. I create this shelf in the bathymetry. Bathymetry is topography of the ocean. I create this shelf to make it slightly more realistic how the water can enter the strait. And then we have everything in between. I'm just changing the depth by 10 meters. You can't see right there, but I'm just shoaling the Bering Strait by 10 meters per simulation. In 3D, it looks like this. So this is our very deep Bering Strait up there. This is completely closed. Nothing's getting through there, I wouldn't think. Okay. And then everything in between. You can see also that spike right there comes out really well in the 53 meters, 43 meters in the middle of the channel. That's those islands. That's the model's representation of the Diomede Islands. It only simulates them as one island. I don't think that matters, but you'll see. Okay. So we changed the topography of the seafloor and we let the model run for 10 years. That's our research procedure, okay? And if we do that, it looks like this. So each data point you see here is 10 years of simulation averaged so that we can look at just how much water is getting through. This is 0. That's 1 sphere drop. A sphere drop is a lot of water, okay? It's an oceanography unit for volumetric flux. And what's important to know about it is that we know in the modern that about a sphere drop of water goes through the Bering Strait. So for our completely open simulation here, 53 meters deep, good. It's right bang on where we want it to be. On the other end of this, we'll start here at the left, our 0 simulation has 0 sphere drops going through it, which is another good news, okay? The water is staying below the water. But looking at these points in between, these 4 in between simulations, I get nervous as an Earth modeler. This looks too good. Those 3 points at the top look exactly the same as each other, but we don't want them to be, or we wouldn't expect them to be. Let's put it that way. I would expect there to be at least some difference between those 3 points. Same thing with these 3. It would be surprising if a 23 or 13 meter deep Bering Strait didn't allow any water through at all. So these look like 0, but are they actually 0? So that one is 0. Good. All good. But let's disentangle this point in particular. This is the one that makes me the most nervous. It's the most like 0. So what I'm about to show you is this point sort of blown up. It's just the flux through the strait through time. Only those, that simulation. And this is what it looks like. So we have 10 years, starting at 0, going up to 10. And then we have the flux on the y-axis here. So we can see we're getting this seasonal peak of water through the Bering Strait. That's sort of what we would expect as the ocean changes seasonally. But we're not really getting very much water at all. This is 0.00025 sphere drops. Up at the peak of this, we're approaching 0.002 spherodrops, which is about a third of Niagara Falls. So water is definitely getting through the Bering Strait, or is in the Bering Strait, when it's 13 meters deep. This is good news. This is very reassuring to me. This tells me that there isn't some sort of instability in the model that's making this 13-meter deep simulation look wonky, look like it's 0 when it's actually not. It's doing a simulation. It looks realistic. That's what you can imagine, sort of just a bay between Siberia and Alaska. So good. So we can now assign a check mark to that data point. We're comfortable with it. It looks good. But what about these other 4? We felt good about our 13-meter deep simulation, so let's just do the same thing with these other 4. Let's put them up on a figure all together, all 4 simulations. And that looks like this. So the blue, orange, and green, those are our deeper simulations. You can see that they all have an average of about a spherodrop, which is what we were seeing in the previous slide. But you'll also notice that they're a bit different. In the green simulation, so that's 33 meters deep, we're getting sort of a lower trough when the least amount of water is getting through. It's more than the other simulations, but it also has a lower peak. So water is getting through the Bering Strait, but the dynamics of it are different. Good. Okay, that's what we were shooting for. Similar thing with orange, sort of an in-between of green and blue. Blue is completely open, looks great. So that's great. Those 3 simulations look great. Does anyone notice anything that looks a little off in this figure? I did too. It's this. This looks like crap. So this is our 23-meter deep simulation. You'll see that it starts off kind of strong, increasing. It's okay for it to be down here to start. That's okay. But it sort of starts to have more water coming through the strait. And then it gets all sort of crinkly. It has these jagged points in it. We want this nice seasonal signal that tells me something's wrong. Then after about a year and a couple months of simulating, or running the simulation, let's say, completely craps out, okay? So from here on, it's outputting data files, but they're full of big fat nothing, okay? You can plot it up and it looks like just a strip of green. So something about this simulation is breaking our model, okay? This is not a real result. It's a sign that something has gone horribly wrong. So those 3, good. We feel confident. This one, not good. Perhaps our most interesting simulation is failing. It doesn't work, okay? This is very disappointing. It's been very disappointing for some months. So what do we think is going wrong? This brings us back to the Diomede Islands. There they are. They were on the cover slide too of this talk. Those were the Diomede Islands. In the model, they're represented by this spike here. It's actually quite hard to see in this figure, so it's that. That spike looks innocuous enough in this representation, but I believe this is what's messing us up. I think this spike, as we make sea level lower, those islands look bigger to the model. And this is creating an instability where the model can't tell if water should be allowed to go through there or not. It's smaller than the grid size of the model, or the island is, but we get this tiny little passageway that the model just can't decide if water should be allowed to pass through there or if it should have to go the other way. And that's what's breaking the model in my hypothesis. So the Diomede Islands are ruining everything. So what is our path forward? What are our next steps? So we're starting with this. We want to fix this data point. So the plan is to eliminate the Diomede Islands, just in the model. It's not necessary to do that in real life. Once we do that, we're going to safely be able to get our final data point for our model, okay? We'll know, does this plot here, which would be great? Does it plot all the way up there? That would also be interesting. Or is it indeed a real 0 or an effective 0? I don't have a hypothesis. I don't know. It's never been able to work, so I wouldn't dare venture a guess. But in order to actually have this curve be useful for future researchers, it's important that we be able to move that data point somewhere in between. Then we'll know with confidence how much water gets through the Bering Strait depending on how deep it is. And that's what we're trying to get, right? And we're almost there. We're, 5 out of 6, not too bad. But we need this last data point in order to tell a complete story of, as sea level changes, how much water gets through the Bering Strait. And in turn, how much water or how much fresh water gets to the Arctic. Now, we ventured far from our premise, which was modern climate change, CO2, all of that. So let me bring you back, okay? With these constraints on flow through the Bering Strait, we can better understand the Bering Strait's role in keeping the Arctic fresh or freshening the Arctic, okay? That gets us at a broader sense of climate change, its relationship to ocean circulation through time. And the through time is the really important thing here. That allows us to test our hypotheses of the impact of this fresh water by looking at climate that has already changed, looking at examples that have already run their course. So that's ultimately our goal here, is to be able to understand the sensitivity of the ocean to changes of salinity and temperature. That's what we're getting at. So my results, that curve that I showed you that shows how much water gets through the Bering Strait, depending on how open it is, will be used by other paleoclimatologists. They'll take those data and they'll put them in the broader context of what we know about climate during the last ice age, let's say, which is the time period we're talking about. That work will then be referenced by people who study modern climate. And this is when, rubber hits the road in terms of understanding future climate change and modern climate change. People who do that work of projecting climate forward, understanding the climate change we're experiencing now, they use paleoclimate as sort of a testing ground. They have a model, they want to know if it works or not. They apply it to a situation that already happened because we know the right answer. With modern climate change, we don't know the right answer, okay? We're trying to predict it. So it's important to have these past examples to better constrain our models and our understanding in general. So the climate is enormous and complicated. The oceans are enormous and complicated. Climate change, what we talked about at the beginning with greenhouse gases, that's not that complicated. But the impacts, what we've been talking about so far today, are quite complicated. So people who study climate, like myself, we typically focus on some smaller aspect of the climate that we can then pass to people who study other aspects of the climate. And in doing this, we get a broader picture collectively altogether as a climate community of how our climate works. So my work doing paleoclimate, modeling paleoclimate is perhaps 10 steps away from what people really want, which is predicting future climate change. So let's look back at our goals, okay? As I start to wrap things up. I wanted to teach you about how the climate works and what climate research looks like. I hope that landed. I hope I achieved that, okay? That's what we spend most of today on. And then I wanted to avoid dread. And one way to avoid dread is by not really talking about the bad stuff, right? I spent most of the talk avoiding talking about the bad stuff. That's why you study paleoclimate. It's not sad because it already happened. But I did, unfortunately, mention modern climate change and how it works. When I showed you this figure of CO2 and how it's been increasing since 1960 with no pauses whatsoever, you probably felt dread. When I showed you this figure of our ocean warming, with only one exception, that's for a very tragic reason, you probably felt dread. And I'll say to you what I say to my climate change class is that there's very little I can tell you to make this less sad. It's true, okay? And I can't really offer you a solution right now. But I can offer you the framing that I use when I think about climate change and about sad things. And it comes from Robin Wall Kimmerer. She's an Indigenous author in New York, in her book, Braiding Sweetgrass. She says, despair is paralysis. It robs us of agency. It blinds us to our power and the power of the earth. Environmental despair is a poison every bit as destructive as the methylated mercury at the bottom of Onondaga Lake. But how can we submit to despair while the land is saying help? Restoration is a powerful antidote to despair. Restoration offers concrete means by which humans can once again enter into positive, creative relationship with the more than human world, meeting responsibilities that are simultaneously material and spiritual. It's not enough to grieve. It's not enough to just stop doing bad things. So though our work, my work, your work, might be 10 steps away from what people care about, it's still important. I do my restoration by studying the climate, studying the Bering Strait, making it shallower, seeing how much water goes through. Whatever you do, it's important. And I think focusing on the restoration and not focusing on the bad things is what's important. And with that, I'll take your questions.
For the sake of Zoom, I'll ask that you wait to get the microphone.
So, once you figure out your island problem, are you gonna run the simulation with more like specific depths in between, say 13 and 33 meters?
No.
No?
So I can't. I don't actually, yeah, I do have a figure that will help with this. If you look, so this figure, hold on. Okay, one more. Okay, these are really smoothed, so they look a lot better than they actually are. But I only have 10 grid cells going down, so I can only change it by 10 meters at a time. So I'd love to, but no, I can't. And I think given what this looks like already, the sort of in between of these is probably more not super important. If it was changing very quickly, that might be more interesting. But yeah, good question. And no, I can't. Yeah.
Other questions?
So last year at the poster session that we did for organic chemistry, we had a guest lecturer who talked about basically doing synthetic photosynthesis. Do you have any thoughts on the work that was done if you attended that lecture?
I didn't, but I can talk about the role of photosynthesis, if that helps.
Yeah, well, this just in particular was, he called it, I believe, a bionic leaf, which was able to do photosynthesis with all of the wavelengths of light, which was very good and very productive, and it is able to do a lot of water. So it's able to be used with any water. And do you think that approaching climate change through that sort of lens, based off of how I imagine you're going to talk about photosynthesis, being able to replicate that is going to help significantly?
So before I answer, do you know what happens to the CO2? Does it go into carbohydrate? Okay, yeah. So I think that's good, okay? Anything we can do to make this, where is it? Well, the Keeling curve, the SAD figure I showed you, less is important. There it is, okay? So that's what these little squiggles are. As I said, that's spring. That's photosynthesis happening, pulling CO2 out of the atmosphere. So if we could increase that process, that would help a lot with this. In general, I'm in favor of carbon capture, pulling CO2 out of the atmosphere. It makes me nervous, but I don't know that we have much of a choice. The issue with carbon capture, and that's sort of what I was getting at with my follow-up there, is the sequestration part of it. It's pulling CO2 out of the atmosphere is one thing, but storing it safely in a way that it's not gonna go back into the atmosphere is the concern. So short answer, yes, I'm all for synthetic photosynthesis. Longer answer, anything to remove CO2 and importantly, store it away for a long time.
Other questions?
Why is there an arctic blob not?
So Emrys
Why
asked,
is there?
yeah, Emrys asked me, why is there an Arctic blob and not an Antarctic blob? And it's a little bit of a complicated answer. The short one is that Greenland is melting much, much faster than Antarctica. Antarctica is a lot bigger. It has a big ice shelf around it that kind of holds it in place. Greenland is smaller, so it melts much more quickly, so we get more meltwater from it. The other part about this is that there's a really important current that goes around Antarctica called the Antarctic Circumpolar Current that moves very quickly. So this blue that you see here, that might actually be a little bit of Antarctic melt, but you wouldn't form a nice little blob in the same way because that water would be moved more quickly. The Atlantic, meanwhile, has a gyre, so a swirling surface current that tends to sort of trap stuff within it.
Any others? If not, please join me in thanking Michaela again.